Okay, so last time I explained the concept of improper integration. Now, just maybe to point out one fact, because normally students tend to believe that if you have an improper integral of first type, if the integral is divergent, then it must be equal to infinity. This is something, because if you think about an area, if you think about the improper integral of type 1 is computing an area. So you have a function f of x, let's say for x is larger or equal than a. So you can depict this as, okay, so here you have an a, and then you have a function like this here. The function has to tend to 0, otherwise you see that the area will be infinite. But you see here, if you if you compute the improper integral from a to infinity, f of x dx, okay, you can interpret this, in this case, where the function is larger or equal than 0. So for this situation, you can interpret it, this integral as an area. Okay, and then it's pretty clear that either the area exists or it does not exist. If it does not exist, the area must be equal to infinity. Okay, so here you see, if the function f of x is larger or equal than 0, this integral either convergent or divergent, and if it is divergent, it will tend to infinity. Okay, so the divergence will be very special. Okay, because many integrals which we encounter are of this type, so students easily tend to believe that whenever an improper integral is divergent, it must tend to infinity. But this is not true. This is of course not the case. For instance, if you look, a very easy example is this one. Okay, because this function is not larger or equal than 0, you cannot interpret this as an area. So you see, by the definition, this is the limit t tends to infinity of the integral from 0 to t cosine of x dx, which is the limit as t tends to infinity sine of t. And this limit does not exist. Okay, it's not equal to infinity. Okay, so because sometimes you see that in some textbooks you see that in some textbooks you see that if this integral is divergent, okay, the author normally expresses this as by this symbol here. Okay, but this is just true if f of x is larger or equal than 0. Okay, then you have two cases: either smaller than infinity, which means convergent, or equal to infinity, which means divergent. But if f of x is a general function, okay, of course you can use this in order, if you interpret this as the meaning of this symbol is that this integral is divergent, it's okay, okay? But in the general case, as we see here, it's not necessarily true that this integral must be equal to infinity. There can be other types of divergence, as we see here. This is another type of divergence. The limit does not exist, okay? But it's not necessarily equal to infinity. So you just should keep this in mind. But as I said, for this special case, okay, it is pretty obvious from the area interpretation that the integral either is convergent, or if the integral is divergent, it must be equal to infinity. So the divergence is very special. Okay, but actually not so easy to prove. It's not so complicated, but we are missing one fact in order to prove this. Okay, but so if f of x is larger or equal than 0, you could prove a theorem which tells you that this integral is either convergent or it diverges to infinity. Okay, so you see sometimes, you see this quite often, that also use this kind of notation in order to denote divergence, and then this notation in order to denote convergence. Okay, but strictly speaking, this is just correct if f of x is larger or equal than 0. Otherwise, you can interpret this just as a notation. Now, but essentially what I want to talk today, so we spent now the last few weeks talking about integration techniques. Now, I told you already that several times that the task of integration normally more complicated than the task of differentiation, because of the new situation that there might be an integral which looks quite easy, but you cannot express this in terms of the function you know. I already told you several times, for instance, the integral e to the x squared is of this type. now, if you encounter such an integral, which is also important in application, the only method you have is trying to approximate the integral. So you need some numerical methods. Now, I just want to briefly talk about such numerical methods. We already learned one of them, namely midpoint rule, but there are also a couple of other numerical methods which are important in order to find integrals where you cannot find an antiderivative. Or in applications, there might be another situation, namely that the function is not given by an expression. The function is coming from some data. So you just have data. And in this case, of course, you cannot use our usual approach, which is using the fundamental theorem of calculus. So also in this case, the only method used, which is left, is approximation. Now, the reason why I just talk roughly about this is because there is a own sub-area of mathematics called numerical mathematics, which studies such kind of questions. So here we will just look at some preliminaries. So this is the section 7.7 in our textbook. Now, if you want to approximate the integral, actually from the definition you have already a natural way how to approximate the integral, namely you just approximate it by the Riemann sum. Okay, so you choose a large n, and you compute this instead of the integral if you cannot compute the integral. Now, you see already from this kind of statement of the method, okay, there's several questions which are interesting arise, namely, okay, how large to choose the n such that you get a certain amount of precision, such that the result you get here approximates the integral you want to approximate sufficiently close. Okay, so one important question is, okay, how to choose the n? And normally you do not know the value of this integral. Otherwise, you do not need to use approximation. Now, another question is, okay, what is a good choice for because here you have still freedom. Okay, you can choose the sample points. So another question is, okay, how to choose the sample points. We saw already that possible choices are you choose the left endpoints of every interval. Okay, which is called the left endpoint approximation. Okay, so here you choose xi. So the sample points, you choose the left endpoint of the interval. No, in our textbook, this will be denoted by ln, left endpoint approximation. Now, there is also a right endpoint. Approximation. Which, okay, you choose, as the sample point, you choose the right endpoint. This is called Rn. And there is another one which we already introduced earlier, namely midpoint approximation or rule. Here you choose as sample points the midpoint of the ith interval. And this we denote by mn as previously. And we saw already, actually, this rule should be the best one, okay? In the sense that, because you have the freedom here of choosing the sample points, and we saw already that roughly the best choice should be this one. Okay, the reason for this, the intuitive reason, okay, just to explain this once more, we have seen this already earlier. So if you look at the ith subinterval, okay, so the function, our f of x on the ith subinterval maybe might look like this here. Okay, so you see already from here that if you choose the midpoint, this gives you a better approximation than choosing left or right endpoint, because if you choose the midpoint, then you approximate the area below this part of the function and above the x-axis by this rectangle here. It's kind of from here to here you overestimate the area, and from here to here you underestimate it. So it should kind of average out, and it should in the average, okay, this should be a better approximation than choosing the left or right endpoint. Okay. Of course, you could object and say, but our function is not necessarily, because this, of course, this kind of reasoning just holds if our function is increasing or decreasing. And you could say, but our function can look much more complicated. But this interval is tending to 0. Okay. And if our function is, because our function has to be smooth, continuous, okay, that this integral exists here. So if our function f of x does not behave too wildly, then if you look at a small subinterval, okay, the function should be increasing or decreasing. Should look like a line there. Okay. So actually, so this kind of reasoning should be true for all functions which are not do not behave too badly. Okay. So in this case, we expect that this rule here, this approximation, should give a much better approximation compared to those two here. Okay, so any questions to this? Now, but there are also other ways of approximating a given integral. For instance, you just use the area interpretation. Okay, so you have a function. Now, let's maybe. Okay, so let's look at this function. Okay, so what we always do is we divide the interval from a to b into subintervals. So let's say one subinterval is this one, the second is this one, the third is this one. Okay, so this is then x0, which is equal to a. This will be x1, this will be x2, this will be x3, and this will be x4, which is equal to b. Now, for all those approximations, okay, we will approximate the area. If we just look at one subinterval, we will approximate the area below the function and above the x-axis by using a rectangle. But for instance, you could say, okay, I choose those 2 points here and just connect them by a line. And then I choose those 2 points, connect them, those 2 points, connect them, and those 2 points, connect them. And now instead of using a rectangle, I use this trapezoid in order to approximate the area below the function and above the x-axis. Okay, this rule, maybe you have seen this in high school. I'm not sure whether you learn such things in high school, but this rule, on every subinterval, you approximate by a trapezoid. It's called trapezoidal rule. I don't remember how to write this in English. Now this rule we are going to denote by Tn. Okay, so we have a fourth rule, trapezoidal rule, or also trapezoidal approximation. Okay, which we are going to denote by Tn. Okay, so you see from this, because you know that this trapezoid, okay, you can easily compute the area, which is f of x0 plus f of x1 times the height half. Okay, so you have a delta x half, and then you have, for this part, you have a delta x half times f of x0 plus f of x1, and you have to do this for the others as well in order to get a formula. So in general, if you have n points here, you will have Tn is equal to, so delta x half on every subinterval, then you have times f of x0 plus, and because you have to count this point here twice, because for this trapezoid and for this trapezoid, so you have 2 times f of x1 plus 2 times f of x2, and you go on like this here, plus 2 times f of xn minus 1 plus f of xn. Okay, so the trapezoidal rule will compute, instead of the integral here, this approximation, and Tn, and we'll use this in order to approximate the integral. Now, you see already from this description, actually you can express the trapezoidal rule in terms of the left end, and the left endpoint approximation, the right endpoint approximation, namely it's just the average of those two, which gives you the same formula. Okay, so actually you can forget about this, that this is larger or equal than 0. For larger or equal than 0, you have this nice picture here. You could similar discuss the case where f of x is a general function, but from this here you see already that, okay, this is a kind of approximation of the integral. Namely, you have those two approximations and you choose the average as a new approximation. Okay, and the question is, okay, because we know already, we can forget about those two here, okay, because those two here are weaker than this one. So the main question is, okay, how does the trapezoidal rule compare to the midpoint rule? Okay, which one is better? This is the main question we want to discuss first. So for instance, if we look at this easy integral here, the example which we use, here we do not have to use approximation, but we can, at least because we know the right value, so we can at least test our methods. Okay, so if you compute for this integral the midpoint approximation, where you divide the interval from 1 to t into 5 endpoints, then you get and if you compute the trapezoidal rule also by dividing the interval from 1 to 2 into 5 subintervals, what you get is 0.695635. Of course, one example doesn't say anything. We also know the right value, ln of 2, which is 0.693147. Okay. So this is just one example. Okay. So this does not tell. Normally, it doesn't tell you anything. But let's just check for this value. Okay, which one is better? You see that the midpoint rule seems to be better. Okay, because the error which you have for the trapezoidal rule is about twice the error for the midpoint rule. Okay, we will see that for this holds for this easy example, but we will see that this holds for most cases. Okay, so you see, for this case, you see, okay, it looks like that the midpoint rule beats the trapezoidal rule. It's better than the trapezoidal rule. Okay, but this is just one example. Okay, so this doesn't, maybe this does not convince you. Okay, because it's just one example. So maybe for other examples it will be different. But I first show you an intuitive reason why this must be the case. Why the midpoint approximation is better than the trapezoidal approximation in general. Let's look at one subinterval. Okay, so we have here xi minus 1, xi. Now, let's assume, again, let's say the function looks like this here. Okay, so if we look at the trapezoidal rule, the trapezoidal rule approximates the area below the orange function and above the x-axis by using the area of this trapezoid here. Okay. Now for the midpoint rule, we use a. So this is about the midpoint. For the midpoint rule, we use a rectangle. This rectangle here. Okay. So this is the midpoint rule. So for the midpoint rule, you use this rectangle in order to approximate the area. Now you see, okay, but you can move this rectangle. You can move this line like this here, because this tells you more about the error. Okay, so you just take the line and move it like this here. Okay, now you see that if I do this, the area of this rectangle compared to this trapezoid will not change. Okay, so actually what the midpoint rule does is to approximate the given area, okay, by the area of this trapezoid here. So you see that the approximation error from the midpoint rule is this here. Okay, so this here is the error from the midpoint rule. And you see that what you see here, this here, is the area from the error from the trapezoidal from the trapezoidal rule. So this is the error. And you see that, at least for this, in this situation, you see that the error from the midpoint rule should be smaller. Okay. You see this is kind of always true if the function, because it's this function, this special thing about this function concave downward. Okay. So you see that for the trapezoidal rule, okay, the approximation will be below, okay, and for the midpoint rule, the approximation will be above, and this is roughly the tangent. You choose the tangent at this point here. Now, you see from this, you tend to believe, okay, that the midpoint rule should give a better approximation than the trapezoidal rule, unless the function behaves too badly, okay, does not behave smooth enough. Here, you still need that the function behaves not too bad on a small subinterval, okay. But since this subinterval for the integration process will tend to 0, okay, locally, if the function is like here, if the first derivative exists and is continuous, or properties like this, the function will locally behave very nicely. Okay, so from this you can roughly, this explanation should roughly tell you that the midpoint rule should give a better approximation than the trapezoidal rule. But of course, this does not. This is no proof, nothing. Okay, but from this we just see now that using because what we do on every subinterval for the trapezoidal rule is we approximate a given function by this linear function here, by choosing those 2 points here. Using such an approximation does not, if you already know the midpoint rule, does not give you a better rule. Now, it's kind of interesting here to look at the error. Namely, we define the error. For instance, we define the error of the midpoint rule as okay, the real value minus the midpoint approximation with step size n. And similar, we define a et by okay, the real integral minus now the trapezoidal rule. So for the trapezoidal rule, you have it's impossible to, you have delta x half, and then you have f of x 0 plus 2 times f of x1 plus and so on plus 2 times f of xn minus 1 plus f of xn. Okay, so this is the error between those between your approximation and the real value, and it's interesting to consider this. Of course, if n is getting larger and larger, its error should get smaller and smaller. But it's interesting to compute this for some values because you see more than the error is getting smaller. You see quite a lot of phenomena from an easy table. So you find the following table in our textbook. We use, as a toy example, we use this integral here, where x is on this interval, which I just approximated before. Okay, so it's our toy example. Now, if you let's also compute the area. We define similar error if we approximate the integral by the left endpoint rule, then for the right endpoint rule, we know already this one is better. This one is better, and also for this one we do not know it because this one is not so good as this one. Just to see how all those rules we have defined so far compare to each other. So we have also here then the et, and the final one is en. So you find this in our textbook, but because this is worth it to copy down. Okay. Now, of course, the most obvious thing which you see from this table is that n is getting larger and larger, so I chose here that I always doubled n. So first I started with 5, I doubled it. Okay. As n is getting larger and larger, the error is getting smaller and smaller. This is no surprise because we know by definition, as n tends to infinity, this should approach the integral here. This is the most obvious thing you see from this table. But you see also a few more interesting things. So another thing which is quite obvious are the signs. Here you see always minus, plus, here minus, plus. Also this is no surprise because this function decreasing. Okay, so if the function is decreasing, you choose the left endpoint, you get something which is larger, so the error should be negative. Okay, so the error is always negative because the EL overestimates the area. Here the ER underestimates the area because of the same reason, decreasing. And this here, here the sign essentially, from my explanation here, you see one of them overestimates, one underestimates, and the function here, 1 over x, is concave upward. So you have here in this situation, the midpoint rule overestimates the area, but here you have it the other way around. Here underestimates the area. Okay, so that's why here you have minus, here always plus, here minus, here always plus. Also, this is no surprise. So this is not interesting. It's not so interesting. But what is interesting, what is more interesting is that you see that, okay, we already saw that the trapezoidal rule is not so good as the midpoint rule. You see this also in this table here. Okay, so you see the area is larger. But you see more. You see that the area of the trapezoidal rule is about twice the area of the midpoint rule. I told you this before, okay, but this you see here in general is always true, about twice. If you multiply this with 2, if you forget about the sign, okay, if you multiply this with 2, you get this. If you multiply this with 2, you get more or less this. If you multiply this with 2, you get more or less this. So you see that the area, this error here is about twice. If you forget about the sign, it's about twice of this error. It's quite interesting. Now, what you see as well is that, so those two are both better than, seem to be better than the left endpoint rule and the right endpoint rule. But maybe the most interesting thing from this table is the following. You see, you observe something. If you look at this here, you observe something interesting. You see, as you double n, okay, the error seems to be reduced by a factor of 1/2. Okay, you see, if you multiply this with twice, with 2, you get about this. If you multiply this with 2, you get about this. Okay, and the same is true here. If you as you double n, the error is always half of the previous error. Okay, so you see here that if you make n larger and larger, if you double it, you get a feeling, okay, how fast the error is going to 0. It's important. And for this one, it's quite different. Okay, you see, 4 times this one is about this one. 4 times this one is about this one. Okay, so you see here the behavior is the convergence to 0 is much quicker because as you double n, okay, the error is reduced by a factor of 1/4, and the same here. Okay, and but you can still say, okay, this is for this example. Okay, so maybe if you choose another example, the behavior is completely different. And the answer is no. And for this, we need actually estimates of the error. Okay, so if you try to find estimate of the error, we are not going to do this. We are going to prove such estimates next semester. But I show you the error estimates, and you will see from the error estimates that what I said, okay, can be seen from the estimates, which is the following result. And actually, this is something which you need. You need normally error estimates in order to, in order that the approximation rule gets useful. Okay. Normally, if you do not have any error estimates, okay, it's hard to predict because you do not know. You do not know. Okay. You just get some number for the approximation, and you do not know. Okay, how close is this number to the quantity you actually want to compute? Because you do not know the quantity. Otherwise, you won't need the approximation. Okay. Now. Normally, if you do not have any error estimates, okay, normally you just do the computations, and we normally in a kind of general rule, which is sometimes applied, is that if you do computations, numerical approximations, and you look just at the result which you get, the digits which do not change anymore are correct. This is kind of this is not a real precise rule, okay, but this is a rule often applied, okay. But if you have error estimates, you can normally say more about the error. So normally, if you have a numerical method, what you certainly need are error estimates in order that the numerical method is useful. Now here, for those two, we just look at those two because those two are not interesting. For those two, okay, it can be proved that if the second derivative is bounded on the interval AB, then for the trapezoidal rule, you have k times b minus a to the cube over 12, I think. I think 12. I'm not so sure. Okay, 12. And for the absolute error of the midpoint rule, you get the following estimate. Now, such error estimates are quite interesting. The first thing you should observe is that this is an estimate. Okay, so meaning that, of course, your error could be much smaller. Okay, it does not necessarily have to follow this behavior here. But also from next semester, we will understand that this, for many examples, these error estimates are rather precise. So you can look at the bounds like is equal to almost. Okay. Now, you see here you see the behavior which we discovered here. So you see for this example, you see I said if n doubles, the error is reduced by 1/4. You see this here, okay? If you replace n by 2n, then you get an error which is smaller by 1/4. Okay, and this you really see from this table here. You also see that the error of the midpoint rule, okay, is smaller, okay, as the error of the trapezoidal rule. And the error of the trapezoidal rule is about twice the error of the midpoint rule. So everything you see from this error estimates. Okay, so you see that actually the behavior, because these are upper bounds, okay, the real error does not necessarily have to follow the upper bound, but these upper bounds are rather good, because from this table you see, okay, everything, all the effects we have just discovered, okay, are explained by these error bounds. The really good thing about this bound is, the really important thing is this behavior here. Because you see that if n doubles, then the error is reduced by a factor of 1/4, which means that if you double n twice, you get one digit correct. You get one digit, which is then correct in one more correct digit in the approximation. Because you have 1/16, which gives you one more digit. Also, you can use these error bounds here in order to, for instance, if you have given an example like this one, it can tell you when to stop. And any questions? If you look at those two, this one is smaller, so the error is smaller, so this one is better. Okay, but you have to keep in mind that this is a bound here. Okay, so you have just a bound here. This just tells you that the error, okay, is smaller or equal than this one. But of course, this error could still be smaller than this one if this bound is not good enough. Okay, you understand what I mean? Because this is a bound, the upper bound. Okay, if you compare those two bounds, it does not necessarily tell you that okay, this one will always be smaller than this one. But the important thing is that these bounds are almost sharp. Okay, so you have almost the equal behavior here. Okay. For many functions. So those two bounds predict very well the behavior. And you see this one is better because if you multiply those with this error, so this roughly tells you, if you have an equality sign, this roughly tells you if you multiply this with 2, you get this one. Okay? And you see this is really the case. If you multiply this with 2, you get about this one. If you multiply this with 2, you get about this one, and so on. Okay. You can also use, of course, you can now also use those error bounds in order to, if you have given an example, for instance, this function here on this interval, and you should compute the integral numerically within a certain precision, so something like the error should be smaller or equal than 10 to the minus 5, then you can use this bound here in order to figure out what is the n you have to choose. And because this rule here is better than this one, okay, this n will be normally smaller than this one. You need less computation to get the same error. Okay, so those are two rules here. You should roughly understand that you should understand why the midpoint rule is better than the trapezoidal rule, and you should roughly understand what is the meaning here of those bounds here. And you should also understand that if you do a numerical approximation, you certainly need some bound in order to say something about the error, because you normally do not know what is the distance between your approximation and the real result, because you do not know the real result. That's why you do approximation. So you need such kind of error bounds in order to understand how good is your method. Okay, so we saw that if you choose on every subinterval, if you approximate the function on every subinterval by a linear function, this does not improve your original midpoint rule, because the original midpoint rule on every subinterval approximates the given function by a constant function. Now we chose a linear function for the trapezoidal rule. So maybe you might guess, okay, then let's choose a quadratic function, a quadratic polynomial. So you do not choose only one subinterval, but two. So you have overall 3 points, and you find for every 2 subintervals, you find the quadratic polynomial which approximates the function. You compute the area below the quadratic polynomial instead of the function. The reason why we choose polynomials is because polynomials we can integrate, easy to integrate. And this is called the Simpson rule. So one assumption which we need in order to use the Simpson rule is that we divide the interval AB into an even number of subintervals. Now, okay, so you have some function. Now, what you do is, okay, you always look at 2 subintervals. This is different to the previous rules. Okay, so you look at the first 2 subintervals. Now you see you have here these 3 points. This one, 3 points of the function. Okay, and now you search for a quadratic polynomial. So you search for a polynomial of degree 2. Such that this polynomial at the point x0, x1, and x2 is equal to the function. Okay, so you find a quadratic polynomial. So here maybe it looks almost like this here, because the quadratic behavior would like something like this here. So let's say a little bit different, just that it looks different. Okay, so something like this here, almost. Okay, because you have a quadratic polynomial, so it should be almost like this here. Okay, and now you compute the area below the polynomial. So here, for this subinterval, you compute the area below the quadratic polynomial instead of below the function. Should give you a better approximation. And you do this for the first 2 subintervals, then for the second 2 subintervals, and so on. Okay, this new rule. So this kind of, you have to compare it with the trapezoidal rule. For the trapezoidal rule, you choose one subinterval, you choose those 2 points, and find a linear function. A linear or a first order polynomial. Now you use a similar idea, but you use 2 subintervals and you find a quadratic polynomial. Okay, and the reason why we choose polynomials is for polynomials it's easy to compute the integral. Now, how about the formula for this one? Let's maybe first look at the simplified situation where you have here you have h. Here you have, so this is h here. This is minus h. So let's assume we have 3 points. So here we have y0. Here we have let's call this y0. This is y1. And we have another point, which is y2. So we shift this situation here. Or let's choose the same relative distances that you understand what I'm doing. So first, for simplicity, we shift this here to the origin. So we have here this point, and this point. Okay, so this should be y0, this should be y1, this should be y2 here. okay, so we have to find the quadratic polynomial. Which at 0 is equal to y1, at minus h is equal to y0, and at h is equal to y2. We are not first solving for a, b, and c. We first compute the area below this polynomial. Okay, so once we have found this polynomial, okay, we will use this here in order to approximate. So we will use the area below the polynomial in order to approximate the area below the function. Okay, so we will use this here from minus h to h. Okay, but you see that, you can cancel out this one because symmetric. Okay, and for those two, you can just take the integral twice and go from 0 to h. So you have 2 times from 0 to h, ax squared plus c dx. Okay, so this will give you 2 over 3 a h to the cube plus 2ch. Now we take out h over 3. Then what is left is 2a h squared plus, and here we have 6c. Okay, we still have to find a and c in terms of y0, y1, y2 in order to understand how the rule works. So we see that a of, if we choose this point here, h squared minus bh plus c is equal to y0, then we have, if 0 is the most easiest case, so 0 is equal to y1, we have ah squared plus h plus c is equal to y2. Okay, so from this you see that because what we need is 2 times a of h squared plus 6 times c. So what we take is we add those two here and add 4 times this one. Okay, so we get that 2a h squared plus, if we add those two, plus, so we add those two and 4 times this one. So this one cancels out, so we have 6c is equal to y0 plus 4 times y1 plus y2. Okay, so this here, this one will be, you can replace this term here by this one. And so this tells you, because shifting will not change the picture, okay? So this tells you for the first 2 subintervals, you have to take, because this h here will be equal to delta x. So you have, for those 2 subintervals, you will have a delta x over 3 times the function value at x0 plus 4 times the function value at x1 plus the function value of x2. And you have to add for the other intervals, the contribution. Okay, so overall, you will get for the Simpson rule, which we denote by Sn. So we saw this h here is the length of a subinterval. So delta x over 3. And then for the first 2 subintervals, we have f of x0 plus 4 times f of x1, then plus f of x2, but we have to add the second 2 subintervals. So for f of x2, we will get twice f of x2, then plus 4 times f of x3, then plus f of x4, but we have to add the third 2 subintervals, and we go on like this. So we see we have here 2 times f of x4 plus, and we will go on like this. So for the last one, we have then 4 times f of xn minus 1 plus, and the last one will just be f of xn as the first one. Okay, so this, and n must be even. So this is the Simpson rule. Okay, so for the Simpson rule, if you want to approximate integral, okay, by using this rule here, okay, what you do is you divide the interval AB, the interval AB into sub-intervals, and then because you have on the first point is x0, second x1, x2, and so on, and you choose here once the first function value plus 4 times the second function value plus 2 times the third function value, then again 4, 2, 4, 2, 4, 2, 4, 2, and only the first and the last one is 1. Okay, and this here is the length of the interval over 3. So this is the formula you plug in. You use this in order to compute the the approximation for a given integral. So maybe let's go back to our toy example and check out what this rule gives us. So again, if you have our function is f of x is equal to 1 over x, and you choose here the n is equal to 10, so you choose x is on this interval, n is equal to 10, okay, so you have as 10, you just plug it into this formula. Okay, so for instance, the delta x is 1 over 10, because this is the length of one subinterval, and you just plug it into this formula. What you get is this approximation this one. And if you compare this with T10 and M10, so with the trapezoidal rule and the midpoint rule, you will discover this is much better. Okay, but only for this special case. Okay, so maybe it's not very convincing. So again, we should look at error bounds. Now, here it can be proved. Also, this we will prove next semester. So as for the error bound, if you know for the forced derivative, if you know a bound for the forced derivative on AB, then now the error of the Simpson rule, the absolute error of the Simpson rule, will be smaller or equal than this k here times b minus a to the fifth over, and then you have here 180 n to the 4. Okay, now the most important thing is how to interpret this. So is this really better now than compared to the midpoint rule or trapezoidal rule? We know already the midpoint rule is better than the trapezoidal rule, so we should compare it with the midpoint rule. Now, the most important difference, if you look at those two formulas, so this is here, which is something smaller, but you do not know what is this here. You do not know what this here is. Can be different to the midpoint rule, but we forget about this here. Okay, so you see that the most important thing is here this n to the 4th, because this tells you that if you look at the midpoint rule, for midpoint rule you have n squared. For the midpoint rule, if you double n, okay, then the error will be reduced by a factor 1 over 4. Here, for the Simpson rule, if you double n, the error will be reduced by a factor 1 over 16. Okay, so every time you double n, the error will get smaller by a factor 1 over 16. But 1 over 16, 1 over 10 is one more digit. Okay, so this means that here, roughly in every step, whenever you double n, you get one more correct digit. Whereas for the midpoint rule, if you double n twice, you get one more correct digit. Okay, so here the error should go much faster to 0 as n tends to infinity. So this method should be better. Now in numerical mathematics, this is called, because of this power here, it's called fourth order method, compared to the midpoint rule, which is the second order method. Okay, so because the error goes quicker to 0. And now, of course, you could now ask, okay, so it looks like if we use on 2 subintervals a quadratic polynomial, okay, then everything's getting better, okay? So why not looking at the first 3 subintervals and approximating because then you have 4 points, and approximating the function by a polynomial, by a third order polynomial. You should get something which is even better. Now, theoretically, this is really the case. So if you approximate now on every subinterval by on the first 3 subintervals by a polynomial of order 3, you will get a better rule than this one. Okay, but what you have to take into account is the rules will be getting much more complicated. You have to do more computation. Now, if you have to do more computation, error will also come in from a computation error, which will accumulate. Okay, so normally normally we will stop here at the Simpson rule. We will not go. It doesn't make sense to go to rules of much higher order. Also here you could achieve higher powers. Okay, so these are just a few words about numerical approximation. You see there is, concerning this topic, there is much more than maybe meets your eye if you look at it for the first time. But this will essentially I do not know whether you have to take numerical mathematics, but this will normally be taught in much more details in numerical mathematics. But this is roughly what you see in our textbook. Now, it's maybe also for this Simpson rule, it's interesting to observe that it can be proved that it's not so complicated to prove that the Simpson rule can be expressed in terms of the trapezoidal rule and the midpoint rule by this relation here. So you see that the Simpson rule is for 2n intervals. You can compute it like this here. Now, why is this interesting? The interesting thing here are those two numbers, okay? Because we know that the error of the trapezoidal rule is about twice the error of the midpoint rule, and one is positive, one is negative. Okay, so this should kind of average out the error. So if you look at this, from this you already get the feeling that the Simpson rule should be better than the midpoint rule or also the trapezoidal rule, because it just explores the weakness of those two rules and combines them in a suitable way. So it's quite interesting. I think this is one of the exercises to prove this here. But of course, this is quite easy. You take this formula and plug it in here. You take the formula of the Tn and the Mn and plug it in here and show it's the same. Actually, numerical approximation is a quite important issue because we have quite a lot of integrals we cannot compute exactly. Okay, and for all those integrals, the only way to compute them for us is using numerical approximation. So you just use one of those rules and choose n large enough. Normally, such a bound will tell you how large to choose the n if you have given a certain error in order to achieve the error. Now, then we go on to chapter 8. Now, the next issue, the next application we want to discuss is the arc length. Okay, so what we want to do is we have given a function and we are interested now in the problem of finding the length of the arc here. Okay, so the length of the function you see here. Now, this is similar to the area problem. Okay, so in general, it's also a complicated problem, actually the question is not of finding the arc lengths, but of defining them first. Okay, because we have never defined what do I mean by the arc length of something like this here, of a curve like this. Now, so it's similar to the area problem. Now, and we also use the similar approach. So what we are going to do is, obviously, we divide the interval again into subintervals. Okay, then, so we have here certain points, this one, this one, this one, this one, this one, and this one. Okay, and now we are going to, what we can do is, like we have seen for the trapezoidal rule, we approximate the function by a linear function. So we approximate here the function by this linear function, here by this linear function, by this linear function. I should draw this once more because it's not curved enough. I should draw a curve which is more curved. Okay, so let's choose this one. This one is better. Okay, so this one, this one, this one, this one, and this one. So on every subinterval, we will approximate the given function by a line, and we will compute the length of the line, something which is easy, trivial, because we can use the theorem of Pythagoras for this, in order to approximate the length of this line here. And then we make the subdivision smaller and smaller, so it's always the same approach. Okay, so such a set of lines which is connected like this is called a polygon. So we will compute the length of the polygon instead of computing the length of the curve, and then we will make the subdivision smaller and smaller. Okay, so if we denote by L the length of the polygon, if you denote those points here, let's say this is P0, this is P1, this is P2, this is P3, this is P4, and this is P5, then what we have to do is, okay, we have to compute the length of the line between the point Pi minus 1 and Pi. Okay, so this will be the length of the polygon. Now here, this of course is easy. We can use Pythagoras, or the length between 2 points. So we have xi minus 1 square plus yi minus 1 square. So we have to sum over such quantities. And now the arc length, so the length of this arc here. Okay, so S will denote the length of this arc, will be the limit as n tends to infinity of such a sum here. Now, what we assume is that f of x, so let's assume that the derivative of f of x is continuous on AB. So we assume that the function is differentiable on the interval AB and the derivative is continuous. Okay, so such a function sometimes is called smooth. Or the book calls it smooth. Okay, a function which is differentiable and the derivative is continuous. Now, if you have this assumption here, okay, so if you look at this distance here, you can write this as okay. So this is the square root of maybe I should. If you have this, then you can certainly apply the mean value theorem. Okay, so you know that because this here is f of xi minus f of xi minus 1. Okay, if you have this assumption here, you know, okay, this will be equal to f of xi at some point between xi minus 1 and xi, and this will be our sample point times xi minus 1. Okay, so for this assumption, you have this here. So we're going to plug this in here. Actually, in order to have this, we just need that the derivative, that f is differentiable and continuous on the interval. We do not necessarily need that the derivative is also continuous. Okay, so this is actually even more than we need, for this here. Now, but you see, if you have this here, so then this here can be rewritten to, okay, so you have the limit as n tends to infinity, sum I from 1 to n. Okay, so you plug this in here, and you can take out xi minus 1. So you have the square root of 1 plus the derivative of f. This should be the derivative here. Sorry. The derivative of f at xi times xi minus 1. Okay, but this here we always denote it by delta x. Okay, so this is the limit as n tends to infinity, sum I from 1 to n, the square root of 1 plus. So the sample points here come naturally from the mean value theorem times delta x. Okay, and you see now this is a Riemann sum. Okay, so you can use the integral to express this. So this is the integral from a to b, the square root of 1 plus the derivative of f of x square dx. So you see that this here actually, this here is actually the definition of the arc length. Okay, we define the arc length by this limit here, and we see that we can use the integral in order to compute the arc length. Okay, so this is sometimes called the arc length formula. You also see now why I need that the derivative is also continuous. Because if the derivative is also continuous, this function here will be continuous. So the integral will exist. The limit will exist. Okay, so I need this for the existence of the integral. Now this formula here is in our textbook called the arc length formula. Okay, so if you have to compute the arc length of a given function, this is, you just plug into this formula. You just use this formula in order to compute it. Now, you see already from the arising integral, okay, that even for easy functions, the integral you might get here can get very complicated. Okay, because you have the square root and so on. If something like 1 plus x squared and the square root, no problem for us, because we have trigonometric substitution. But if you look at a slightly more complicated function, this integral will become very quickly not solvable. So for instance, let's try to compute. Let's look at the hyperbola. Okay, so you have x times y is equal to 1. And let's say we want to compute the arc length. From, let's say, the point 1, 1 to, let's say, 2, 1/2. Okay, so what you have is y is equal to 1 over x. So you see that the derivative is this one. Of course, you just have to plug it into the formula. So s is equal to, so the x goes from 1 to 2. And you have the square root of 1 plus dx. Now, this integral looks not so pleasant. Okay, so you see that of course, you can simplify this to this integral here. If the x would be x squared, it would be easy. Okay, because if the x would be x squared, we could use trigonometric substitution. But this here looks complicated. I will show you in a few minutes. That's why I brought a computer, whether Maple is able to do it or not. I just tell you this, we cannot compute this. So even for the hyperbola, okay, we cannot find the arc length. Now, another example, just to collect a few examples. Of course, you might now be interested in some of the arc lengths of some easy functions. Okay, this would be an easy function. Okay, but here we cannot compute the arc length because of this complicated integral. Another example would be also an easy function, maybe the sine. Okay, and you go from, let's say, you are interested between x and, let's say, pi. Okay, so what is the arc length of the sine between x from 0 to pi? Now, also here, okay, you plug in. So you first compute the derivative, which is the cosine. And now you plug in. So the arc length is equal to the integral from 0 to pi. And now you have the square root of 1 plus cosine square of x dx. Also this does not look too easy. But this is a very easy function, sine, okay? And you just want to know, okay, what is the length of the arc from 0 to pi? So similarly, you can try the ellipse. Okay, so what you are interested in would be okay. You wanna know, okay, what is the length of this arc here? Okay, for the ellipse. Now, if A is equal to B, if the ellipse is a circle, easy. We know it already since elementary school. Okay, and but for the for the general case where A is not equal to B, okay, the integral you encounter here, you will not be able to solve it. Only for the case where A is equal to B, you can solve it. Okay, which gives you then the usual formula for the circumference of a circle, which is 2 times pi times r. Okay, so only if A is equal to B is equal to R, you can solve it. Okay, for the other cases you cannot solve it. You can try to write down the integral. I think it's one of the exercises in the textbook. So you can try to write down the integral. You will see it's for A is equal to B. Indeed, you will solve it. You will be able to solve it, but not for other cases. This is maybe not the best way that I first discuss many examples where you cannot solve anything. Okay, we should first look in the textbook. You find some examples actually where you can compute the arc length. Okay, it's not that you for every given function you cannot compute the arc length. Now, for integrals, you type this here, int. And then, okay, this integral here. So you have the square root of 1 plus x to the 4 over x squared. And you have to tell Maple, okay, with respect to x. Okay, so Maple is able to compute it. But if you check out the answer, okay, there are two functions which you haven't seen before. Okay, which is called elliptic f and elliptic e. Okay. So Maple is indeed able to compute it. You are not able to compute it. Let's check the other one. The other one is cosine square. Okay, again, Maple is able to compute it. Again, there is a strange function, elliptic e. Again, like the first one. Now, this is quite interesting because maybe you see for arc lengths, okay, it was like you see here the hyperbola, okay, the arc length of the hyperbola, we cannot compute it. Like historically, the first question was to compute the arc length of the ellipse. Okay, so this was historically the first question. Next time we will see because you know there are three conic sections, so-called conic sections. One is the parabola, hyperbola, and the ellipse. Those three. Okay, you have learned them in high school. Next time we will see. Only the arc length of the parabola we can compute it. The others we cannot compute it. Now it was a historical question to compute the arc length of the hyperbola of the ellipse. Not possible. Okay. So the integral which arises is a new integral. Is a new function which is called elliptic e. Okay. So this function you see over there historically just arose from this question here. Okay. So because I haven't written this out, so normally because if you cannot solve this, okay, if you cannot solve such an integral, but this integral here is important. What we often do in mathematics is, okay, we give this function here, because we know that this here is an antiderivative. We indeed know that this here would be an antiderivative of this function here. In order to solve this here, we would need this antiderivative. And if that antiderivative cannot be expressed in terms of easy functions, we normally give it a new name in mathematics. Okay, so you will define a function which is defined like this, and then you can express the answer in terms of this function. This is essentially what happens here. So for the first one, so we will there is a function which is connected to the arc length of the ellipse. Okay, and the arc length of the hyperbola you can express in terms of these functions here. If you're interested in those functions, so-called elliptic integrals, then you can either check Maple. So Maple has a help if you are really eager to know how this function is defined. You go topic search. I'm not sure whether Maple explains it, so but let's try to check it out. Elliptic. Here you have it, elliptic e. So this one. So this topic search is quite useful if you just roughly know, okay, what do you want to find? You just plug it in here, like integral. If you want to know something about how to find integrals, so you have here this elliptic e. Now, okay. Now, normally you will also have some definition. You have here some explanation how to use this. And you have a definition here. So this is called the incomplete elliptic integral, which is defined via an integral. Okay, you see that there is a function so this function elliptic e of x is defined as the integral from 0 to z. Wait, this is z here. But you have a second parameter. I think k and z. Or the other way around. And then you have the square root of 1 minus k square t square over the square root 1 minus t square dt. Now this function, if you know this function, okay, if you accept this function as a function you know, you can indeed compute the integral of the you can indeed compute the arc length of the ellipse. You can express it in terms of this integral here. Okay, this was historically the origin of this function, because we couldn't historically they couldn't compute the arc length of the ellipse. Okay, so they just said, okay, let's call this antiderivative, which we cannot find, a new function. Okay, this one. And Maple indeed knows those functions. Okay, so for Maple it's possible to compute the arc length of the ellipse, but since you haven't learned this function, since you do not know this function, you're not able to compute it. Okay, but of course you can use Maple in order to. Your calculator does not have this function, but Maple has the function, so you can use Maple in order to evaluate this function. It's just a question of acceptance, whether you say, okay, you accept this new function. If you accept this new function, the arc length here becomes solvable. The question of the arc length here becomes solvable. If you do not have this function, this problem is not solvable. But next time I will show you more examples of arc lengths where we actually can compute the arc lengths. But since the formula involves the square root of 1 plus the derivative of a function, okay, so normally the integral you will encounter here is very often for many, many functions is too complicated to compute. And you just can use numerical methods, or you can use Maple, who knows more function than your calculator knows.